So our next step is to talk about functions, now that we've talked a little bit about lines in the coordinate system. So what is a function? We write functions as f of x. That is a function of x, which, and then we give it some value. And we'll say this equals something. Now, really what you're looking at is, because almost every function can be graphed, f of x is often in a single variable function. We say y equals f of x. Let us say we say y is a function of x, and where x is something like mx plus b. So that's a sample function. But what is it exactly, right? What is a function? And really, a function is just a rule. So you can see chapter 2 is all about functions. It starts on page 147. And the definition of a function on page 149 says, a function f is a rule that assigns to each element x in a set A exactly one element, called f of x, in a set B. Now what does that mean, right? It means that for every x value, so what it means for every x value, there is only one y value. So whatever value of x, excuse me, whatever value of x you have, you can put into a function. It will give you one specific value of y. And all of these values of x are called the domain. So a function has two other attributes. As a domain, has a range. If you look at the definition, this is set A, and this is set B, which means this is all x's, and this is all the y values possible. So the domain is anything you can put in for x. And the range then is anything you can put that spits out for y, because y is determined. It is not independent. So in this case, to clarify that, whenever we put a value into this function for x, we're talking about the domain, and any possible choice is in the domain of the function. And anything in this domain, because there is only one y value for every x value, will give you the range of values possible for the function. So we can pick, an equation. So the book says analyzing a function. So let's do that. Let's clear this and let's analyze a function. So I'm going to give you we'll just use the first example from the book for now, which is f of x equals x squared plus 4. So if I say I want to analyze f of x equals x squared plus 4. Okay. So what is this? All right, so let's we could find some values. I could try to graph this, but that's actually the next chapter. So what I'll do is I'll say, well, what are the possible domain? What's the domain of this function? If it's not given, I can find any value of x. Really, any number will allow this to be a function. And by a function, I mean if I were to graph this, it would look like this. It is a parabola that crosses the y-axis here at x equals 4. That is to say, if I plug 0, so this is the point, 0, 4. Because if I were to say x equals 0, I would have f of x equals 0 plus 4. And in this case, I have y equals f of x. All right, so this is what this function looks like. So if I were to take a value of x, and I were to say, what happens, if I eval at, as the book does, f of 3. So this thing here, instead of saying f of x, I say f of 3, which means all of the x values in this function should be 3. That means f of 3 equals 3 squared plus 4. So 3 squared plus 4 is 3 times 3 is 9, plus 4 is 13. Now, an interesting thing about a parabola is that if I said f of minus 3 equals minus 3 squared plus 4, that's still 13, which should make sense because I have a value of f of 3, it has a certain point on the parabola. But if I go the same distance negative, it has the same y value on the parabola. This is okay. You can get the same y value from multiple x values. Remember, a function says for each x, there's only one y. For each y, there could be any number of x values that give you that same. Any number of x values can give you the same y value. That's okay. So the issue is, as long as you just put a number in here for f, and you solve, it gives you an equation that you can evaluate. As long as that has exactly one answer, you have a function. Another way to look at it is, if you can do so graphically, like on this, is what's called the vertical line test. That means if I can draw a vertical line anywhere through this function and only hit it at one point, then it's a function. So we say vertical line test. And I'll say if a vertical line intersects the graph of the equation only once, then it is a function. So for example, if I had some kind of something like this kind of a curve, and this is a sort of curve that could exist. This could be a shape, right? So a lot of times, so shapes aren't functions, right? Because I can go, okay, it's a function there, but now I have problems, right? Because now I'm running it into multiple points. However, this is the sort of thing that can be called a piecewise function, right? Because if I look at this function and I cut out those parts, on this side of this blue line, this is a function. And on this side, it's a function. And that will be on, you can see 151, example 3, a piecewise defined function. And how it looks is it gives you a particular form. So if I say piecewise defined, and let me write this one exactly as it is. I can say C of x, because it doesn't matter what you call f. They like to do this. So this example tells us this function, C of x, and you can use any letter here. Anything that's of this form, one letter with x in parentheses, is going to be telling you it's a function. The most common one is f of x, but you'll often see g of x, h of x, etc. And this says C of x is 39 if x is between 0 and 2 inclusive. That is, say if x takes a value from 0 to 2, so this is the domain, or C of x is 39 plus 15 times the quantity x minus 2 if x is greater than 2. So this has piecewise defined means that it has a domain. It has a value that's different in different values of the domain. So essentially, this function has these two domains. It has domain of x from 0 to 2 and x greater than 2, which means there are no negative values of this function at all. So the range of this function, right, is all positive numbers from 0 to infinity, because that's what we have here. We exclude all negative numbers. And if you were to take some values, right, if I were to say, evaluate this equation, eval function at, say, 1, 2, 3, and 4. Evaluate at these 4 points. Let's see. So C of 1 is between 0 and 2. So that's 39. C of 2 is between 0 and 2 inclusive, right? Because this is a less than or equal to sign. So that's 39. 3, I have to do this equation. C of 3 equals 39 plus 15, 3 minus x. And C of 4 equals 39 plus 15, 4 minus x. Sorry, 4 minus 2. Minus 2. Right? Because it's x minus 2. So x is 3. So I can do this. 3 minus 2 is 1. So 15 plus 39 is 54. And here, 4 minus 2 is 2, so that's 30 plus 39. That's C of 4 is 69. And so that's all a piecewise defined function means. It just means it's one function that, depending on what the x value is, it's going to have multiple ways of describing it. And one of the reasons for a piecewise function is because it must be defined this way because of a situation like this, right? So if this function says, it just says, doesn't matter what the x value is here, it gives you the same y value all through this point. And then it starts giving you higher and higher values. And it gives you them linearly. So if I were to graph this by removing this, and my parabola, right? If I say x is 0, so here's 0, and then y is here at 39. So we're going to start there. And then I say, okay, if x is 2, so if x is 1, I'm here again at 39. And you don't have to write these because I don't want to go on a coordinate system that is to scale, right? In this case, I'm going 0x, 1x, 2x, At 2x, we jump up to 54. And then we jump up to, say 6, 9. And what I have here is I have a line and then a line. No, that doesn't look very good. So let me write like this. And you can see that I have x is 1, x is 2, and then it shoots up. So it changes at that point, too. That's sort of the graph. And I had to lean over my table to do it, so it's not very pretty. Now, we talked about the domain. I mentioned because of that there's the range. There's lots of other things we can do with functions. You can find the difference of a function. They call it the net change. We don't need to go into that too much, but I'll write it down. So here's piecewise defined. And I'll just make a note here. So we could have, say, net change, which is given that is to say, you take any two values on the function, so long, and the net change is f of b minus f of a, so long as a is less than or equal to b. And an example of that is if I were to say, find the net change from 2 to 4. This is A, this is B. So I would evaluate f of B minus f of A. So let's put that in. So I have f of B equals 4 squared plus 4, square brackets, minus f of A is 2 squared plus 4. All right. So 4 squared is 16, plus 4 is 20, minus 2 squared is 4, plus 4 is 8. So from f of 2 to f of 4, my net change is 12. So the value of the function changes by 12 when the domain changes by 4, in this case. So you can resolve this by using this formula. So whenever you see net change, you just do this. And here's an example of such. Now, there's lots of other things, as I just said, that you can do with functions. There's lots of other things you can be asked about the domain, the range. There's the ways to represent a function, and represent just means ways. I'm going to talk about it. I'll mention briefly the 4 ways on page 154. Verbally, I say a description. Algebraically, the preferred method, you write down an equation, like f of x equals x squared plus 4. Visually, you could graph it, like I did when I wrote that parabola. Or numerically, you could just write down or a bunch of numbers in a number table that gives you a series of ordered pairs that are all on the function, that are all points along the graph of the function. That would be by far the most tedious method. Preferably, we want to use the algebraic and visual methods. In this class, I'm going to avoid, as much as possible, using verbal or numerical descriptions. Because this class is to prepare you for calculus, and in calculus, you're going to be using graphs and equations, not these other methods. I haven't talked too much about graphing functions, because that's something more covered in algebra, and I want to talk about values of functions more so than that. Now I'm going to leave some of this, like for instance, what is an even and odd function, the sums and differences of functions. So an even or odd function, you can tell if a function is even or odd. And this is simple. If an x value gives you the same y value, then it's an even function. For instance, if I look at even and odd is on, just had it here. Did I jump past it? So I can tell you what page it's on. Perhaps, more perhaps. Seem to have lost it. So a function is even if it is symmetrical. A function is odd if it is not. So what that means is if I have a function that looks like this, if I have a function that looks like this, if it's symmetrical about the y-axis, these functions are even. These functions are odd. Now, these are some graphs you should get used to seeing. This is a parabola. This is the cosine. This is the line, y equals x, so a line with a slope of 1. And this is the sine function. Now, we're going to end up seeing a lot more of cosine and sine because calculus requires a tremendous amount of trigonometry. For the most part, you don't need to know this, but here's a way to find out if it's symmetrical. And by symmetrical, I mean if I give you an x value, it gives you the same y value, right? If I were to pick any x value on this side, and then I were to pick the negative x value, they would both have the same y value, right? So this is the point x equals pi. This is the point x equals 0. This is the point x equals 2 pi. This is the point x equals minus 2 times pi, etc. And I showed that for the parabola already. And as you can see, for a straight line, every x value has its own y value. And every y value only comes from one x value. X is 2 gives you y is 2, whereas x is negative 2 gives you y is negative 2. So those are different y values. So that's the main thing about functions that we're going to cover. There's other things that we'll cover as we start to do, for instance, adding and subtracting functions. We've already kind of done here, right? I've already shown you can add and subtract a function, in this case the same one at a different value. You could also add and subtract two functions. For instance, I could say f of x equals 3x plus 2, and g of x equals x squared plus x plus 3. And then I could say find the sum. Well, that just means I take f of x plus g of x. And to do that, there's a couple of ways I can do it. I can do it by simply writing them down again. But really, the sum means combine them, right? So I can combine these two functions. And I can say, all right, so I have f of x is 3x plus 2, and g of x is x squared plus x plus 3. And now I just combine like terms. I have only one x squared term, so I have x squared plus 3x plus x. So why don't I just write it like this for now? And then I will combine like terms this way and get x squared plus 4x plus 5. And that would be the sum of f of x plus g of x. So just like with anything else, if I ask you to find the sum of two things, you just write down both those things in parentheses, add an addition sign, and then see what you can do to combine them. If I said find the difference, you would subtract them. If I say multiply them, you would multiply them, which you don't do very often. And if I were to say divide, I won't. I'm not going to make you divide functions. It's a thing that in 10 years of being a physicist, I have never done. So you shouldn't have to do it either. And that's that. When we come back, we'll deal with some specific types of functions, the ones that we're going to see all the time, and their particular properties, which is why I didn't go through them now. So thank you for watching.